This is a super difficult concept, and you want to realize when you struggle with it that it was super difficult even for exceedingly gifted mathematicians. Both Newton and Leibniz, who simultaneously created calculus on their own, came up with the idea of the limit, never ever got the formal definition of the limit. They only ever were able to define it intuitively and algebraically. They never even got close to the formal definition. They created calculus in 1690s. Leibniz published in 1692. And the formal definition of the limit was not made real until Augustin Cauchy did it in the 1920s. So we're talking, I mean, this is over 200 years later. It took a really long time. These are very difficult concepts. This is something that you study in the math major course called real analysis. So if you struggle with this, don't worry about it. Everybody struggles with it. I have what I call a template that will help you learn how to write a formal definition of a limit. And I'm only going to give you very basic ones that are exactly like ones that we've done in class. I'm going to spread this material out over several days because I think it's better absorbed a little at a time. So we'll do some today, some tomorrow, some Thursday, and probably some next week as well. I think a little at a time is a much better approach because it really does sort of make your brain hurt when you're doing these. The problem with the idea of the limit is we say that x is getting close to a, and if x gets close enough to a, what does the y value get close to? But the problem is the word close is not mathematically precise. What do we mean by x gets close to a? How close to a? How close does the y value get to the limiting value? We've seen occasions like in the last graph where we had a hole and the limit value was 2, but the actual function value was 3. So as x gets close to -3, the y value got close to 2, but how close is close? We need to make that quantifiable and make it mathematical. So now we're going to break it apart into pieces. And the first piece is the absolute value of f of x minus L. When you see an absolute value symbol, you can interpret the absolute value as the distance between. So absolute value really does represent the distance between. All right. So we're talking about the distance between the function and the value of L. When you have the absolute value of f of x minus L, this is the distance between f of x and L. And then you read the rest of it is less than epsilon. And this is epsilon right here. All right. And these are called epsilon delta proofs. So epsilon is how close the y value is to the limiting value L. And x is going to get within delta of a. So they're called epsilon delta for the distances on the x-axis and the y-axis. So then we look at the next statement, 0 less than x minus a less than delta. This means that x is not a because the distance is positive. This is important because when you have a hole, you can't actually get to the value. If you get to the value, it's not defined there. So you want to make sure that you're never actually at the point. So you guarantee that by saying their distance apart is bigger than 0. So they can't be equal to each other if their distance is greater than 0. So the distance between x and a is more than 0, but less than delta. All right. The distance between x and a is more than 0. You can't be at a, but less than delta. All right. And these are going to be called epsilon delta proofs. And this is the lowercase letter for delta. Epsilon is pretty much the same upper and lower. It's a little bit larger and more straight. Well, it's, I don't know how to describe it. You've got one that looks like that, and you've got one that looks like that, and they're both epsilon. I can't remember which one's upper and lower. I think this is lower. Okay. Now, in order for the y value to get close to L, we need the y value to be less than some arbitrary epsilon. All right. And this y should not be there. All right. So I need to take that out as well. Oh, that's 3 errors I found today. All right. Choose any arbitrary value for epsilon, and the distance between the y value and L has to be smaller than that arbitrary number. So epsilon is totally arbitrary. Epsilon is chosen. Delta depends on that choice. So you will choose how close you want the y value to be to L. So for example, on the last problem that we did, we had a hole at -3, and this was the y value 2, and then we had a displaced point up here at -3, 3. But the limiting value was 2. You'll choose how close you want to be to 2. Do you want to be within 0.1? Well, then that means you could be between 1.9 and 2.1. Or you could choose it has to be within 0.01. And then it has to be between 1.99 and 2.01, or 0.001. And then it's got to be between 1.999 and 2.001. All right. So you can choose how close to 2 you want to be. Once you've made that choice, it's fixed for that problem. And the choice of delta depends on what you chose. And what we need to do is we need to find a delta that forces that to happen. All right. Now, there's another way to interpret the absolute value, which when we take the absolute values off, we can say that it's between epsilon and the negative. So one other interpretation of absolute value, and this is probably something that you learned or should have learned in your college algebra, but probably didn't understand. This means that it's between epsilon and negative epsilon. When you see an absolute value less than a positive number, you can take it out of the absolute value and put it between the negative of that number and the positive of that number. And then if we solve for f of x, we add L to each of the 3 parts, and we end up with this expression right here, right? L minus epsilon is less than f of x, which is less than L plus epsilon. Now on the picture, what that looks like over here is that we've got L at 2, and then we've got L plus epsilon and L minus epsilon, where epsilon is this tiny little amount. It's your 0.01 difference, all right? So this could be L equal 2, and this could be 2.01, and this could be 1.99, all right? So that's how you determine how far apart they are. That's what the L plus epsilon and L minus epsilon mean, all right? We can do the same thing with the absolute value of x minus a less than delta. We can set that between delta and negative delta. So let me create a little space here. I can write x minus a is less than delta, which is greater than negative delta. And then I can add a to all 3 parts. And then I get a minus delta x and a plus delta. What does that mean on my picture up here? That means that when I'm down here on the number line and I'm looking at -3, then I've got -3 plus delta and I've got -3 minus delta. So that creates a range of values around it, where as long as the X value falls within this range, the Y value will fall between L plus epsilon and L minus epsilon. And we're going to look at a applet that does this in just a second. So here's a better picture of what that looks like. We've got a delta distance. Delta is the distance. So this coordinate right here is A plus delta, and this one right here is A minus delta. They're a delta distance apart from A. And as long as you fall within this range, notice that if you go up and hit the graph and then come over to find where the Y value is, it falls between L minus epsilon and L plus epsilon. So pick a point on the x-axis that's between A minus delta and A plus delta, trace up to find the graph, and then move horizontally to find the Y value. It will fall within the range of L minus epsilon to L plus epsilon. This is what we're trying to do. Epsilon is chosen. They set this width right here. And then we have to find the delta that guarantees that all the values will fit within that range. All right, that's our job. So here's the formal definition of a limit. This is called Cauchy's epsilon delta definition of a limit. Let f of x be defined for all x not equal to a over some open interval containing a. It might or might not be defined at a. We could have a hole there. Let L be a real number, a Y value. Then the limit as x approaches a of f of x will equal L. The Y value approaches L. If for every chosen epsilon value, you choose how far to be from L, there exists a delta, distance from a, such that if the distance of x from a is less than delta, then the distance of the function, the Y value from L, is less than epsilon. All right, so we've got some, and that should be italicized right there. Missed that one too. Okay, I'm finding all kinds of errors in this particular one. I must have been very tired when I proofed it. All right, so we're going to pull this apart and we're going to look at each part of the graph. So A is set, the function is set, L is set, and epsilon is chosen. Delta is the only thing we have control over. We have to choose the delta to make the epsilon work. For every epsilon greater than 0, for every distance of the Y value from L, there exists a delta greater than 0. There's a positive distance of delta, the X values, from A. Epsilon is the distance of the Y values from L. Delta is the distance of the X values from A, such that if 0 is less than X minus A less than epsilon, if X is closer than delta to A and not equal to A, then the distance between f of x and L is less than epsilon. Then f of x is closer than epsilon to L. Okay. Now, what do I think you probably got out of all of that? You're probably very confused. All right. So I've come up with another way of comparing the epsilon delta definition in a real world situation that maybe will make a little bit more sense to you. All right. We're going to play Battleship. All right. Like the game. All right. Although, of course, this gets played out in real life too. So this is our battleship over here on the right. And this is a destroyer over here on the left. L is the center of the battleship. Epsilon is chosen to be between the center of the battleship and the front of the battleship. So you can hit somewhere in the sweet spot. Now you might want to be closer to the middle of the battleship when you hit it to sink it. So it might be that if you hit on the very front, that's not going to be enough to bring it down. So you're going to choose an epsilon to make this interval smaller, all right? So you could choose epsilon such that L plus epsilon and L minus epsilon are here. Remember, epsilon is just a distance. This is epsilon feet. All right, from the center of the battleship. A is the location of the center of the destroyer. So A is right here in the middle of the destroyer. Now, delta is a little bit different. Delta doesn't have to be on the destroyer. Delta could be in the ocean. Where does my destroyer need to position itself so that when it fires the missile, it hits the battleship within this range of L minus epsilon to L plus epsilon? Lost my plus. All right, so where do we need to position the destroyer on the ocean and the missile on the boat so that when we fire it, it hits within the right range? Think about not being able to adjust the height of the missile. Let's suppose that the missile height is fixed. If the destroyer is too close to the battleship, the missile will go over the battleship and land in the water in front. It won't hit it. If the destroyer is too far away from the battleship, the missile will come up and will land in the water behind it. It won't hit it. It won't go down. There's a sweet spot on the ocean where, as long as we position the middle of the destroyer within that distance on the ocean, when we fire the missile, it will hit the battleship within the sweet spot of the battleship and sink it. This is horseshoes and hand grenades. When you throw a hand grenade, you do not have to throw it on top of your target. It could be close and still blow it up, but how close is close enough? That's exactly what we're trying to find out with an epsilon delta definition. How close is close enough? All right. So when you're looking at this picture right here, you can see that they've made smaller and smaller regions for delta. And as they do that, the epsilon values decreased as far as how far apart from L they can be. So if you want to be closer to L, then you have to be closer to A. So if we make epsilon smaller, then we'll have to make delta smaller as well. Okay. So in the notes, you'll find there are 2 applets for the epsilon delta definition of a limit to help you get a better feel for what's happening. So if you click on those, they should open up and you'll see something like this here. Now I'm scrolling in to make it a little bit smaller so that it shows up a little bit better on my screen. And when you're looking at it, we're looking at the graph of the square root of x minus 1. On the left-hand side is the slider bar. And on this slider bar, you'll see that it's setting different epsilon values. So it's starting right now with an epsilon value of 1. What does that mean? Well, the limit value at 5 is 2. In other words, as x is approaching 5, then the limit value approaches 2 because 5 minus 1 is 4 and the square root of 4 is 2. All right. So when we're looking at these, the epsilon is how far away from the 2 you can be. So right now, epsilon is set at 1. Let me close the window so it's not so bright. That's a little better. Okay. So what that means is near the limit 2, I can go within 1 above up to 3 and within 1 below down to 1. And that creates this yellow band that you see all the way across the graph. Now, what we need to do is we need to find a delta that will get it to fit into that position. So now we're going to click on delta, and that creates a sort of purplish blue band that you see right here. And what we want to do is we want to test different values of delta to see if that lands us fully within the yellow band. So for example, if I take any X value here and I go up to the graph and then I come across to where it hits, does it hit within the yellow band? So let me make delta a little bit larger. Right? Now, do you notice how over here on the left side, we've got this red showing up? What this red is telling me is that if I were to choose one of the X values here that's just above 1 and below 2, when I trace them up to the graph and then I move across to the Y axis, their Y value is not falling within epsilon of 2. So that's not falling within epsilon of L. So the trick of it is you've got to play with the delta until you're sure that you've got every value of X fitting within that band. All right. So you can kind of go, now, could you go narrower? Yes, of course. You can always go smaller. You can't always go bigger, but you can always go smaller. So definitely all of these X values that you see here in the purple band, if you trace them up to the graph and then trace across horizontally, you'll see that their Y value is falling within that yellow band. All right. I've never played with the test. I'm not sure what the test does. Okay. Test just tells you where a particular point is falling. So if I want to test this point right here, interesting. How do I get the test point to move? There we go. If I'm testing the point, do you see how I'm testing to see whether or not it's in that range? Right? Now, if I were to take it outside of there, see that I can still fit this within the yellow range, which tells me that delta can be wider than it currently is. So I can move delta until it's larger and covers up that point. Then I can take my test point and keep moving it until the Y value is coming close to the edge. Now, when I get up to here, you'll see that I'm really close to the edge there. All right. So I'm going to move delta until it gets close to that edge. But what happens when I get close to the edge on the top side is that I'm way off on the bottom side. Does everybody see that? It's not symmetric and it doesn't need to be. So when I get up here, notice that this point is now out of the range because it's turned red, but it is the edge of the range. So if I make delta just slightly smaller, then all the values on the upper end will fit with Y values that fit within the yellow band on the upper ends. See how they all turn green? The problem is the lower end. If I come down here, these values have Y values that are not within epsilon of L. So now I have to adjust the lower end of the level, and I've got to make it so that these values fit within the band. So I'm going to move until it turns green. Right there. So now I need to move my delta until it's at least that small to get in all the ones on the left side. So the ones on the right side would fit earlier, but the ones on the left side will not. So I can move it maybe. See, that's still off. So I still need to move it a little bit smaller, maybe 2.8, right? Something like that. If I get it down to 2.8, then it fits in on both ends, all right? So this is what we're doing with the epsilon delta definition of the proof. Epsilon is set, and once epsilon is set, I try to find the delta so that it will fit within that range. Now, if I change epsilon, I've got to start all over. So let's change epsilon, and we'll make it smaller. We'll make it 0.5. So this makes my band much, much narrower. So I'm going to use the test point again. And I'm going to start here on the left side this time. And I'm going to move this until it's right there. It turns green. And then I'm going to shrink delta until it fits inside of that green. All right. Now I'm going to test on both ends to see if all the y values fall within that narrow band, and they do. And that means that delta can be 1.7 if epsilon is 0.5. So again, what you're doing is you're picking the value of epsilon, and then depending on what you pick for epsilon, delta depends on that epsilon, okay? Questions about how the applet works and what it's trying to get across to you? It's a pretty straightforward applet, but the concept is not straightforward at all. It's quite complicated.
I do have a question.
Okay.
But not more or less regarding this. Do we have to prove a limit? We will have to prove a limit by its formal definition?
Yes, you will have to prove a limit by its formal definition, but we haven't done it yet. So we're just still getting a feel for what it means when you have a limit. Now there's another applet over here that does a similar thing. It has directions. It says check on the point box and set your value A by moving the point that's on the screen. All right, now A is this little point right here, I think. So you can set your value of A, and I'm going to set mine, I don't know, right there, I guess, just because. And I'm going to make my graph a little bit bigger. There we go. And then we're going to set on the define Y box and set our epsilon. So we click on define Y, epsilon equal to 0.5. If I make epsilon smaller, you see how it shrinks that band around the Y value. So I'm going to stay with an epsilon of 0.5. And then it says check on the define X box to move the delta until we see the function in the blue region. All right. So now we've got this region around X, which is colored yellow on this applet. And we want to make sure that all of the values that are in the yellow band have Y values that are in the blue band. And they don't, because this one right here has a value that's falling outside of the blue band. So what I want to do then is shrink my delta and make my delta smaller until all of the values that are in there have values that fit within the band. And it's kind of touchy. Okay, there, that works. All right. On this particular applet, Tuatdong made them turn red instead so that you could see the section of the graph with the Y values that are falling inside the band. So this red section right here corresponds to the Y values for the X values in the yellow band right down here on the X axis. So this red band is completely within the blue. So if epsilon is set to be 0.5, then a delta of 1/3 will work. All right, delta of 1/3 will work. And then on the practice one, and this is something you may want to use when you're doing your homework, on the practice one, you can actually type in a function if you want to check a particular function, like on some of your homework, you can type in a function, it will change the function and do the same thing. All right. So both of them very nice applets, and you have links for them in the lecture notes. They should work in both the PDF form and they should work in the Word form, but you may have to download them in order to get them to work. Right. We're now ready to talk about how to actually prove this. So we're going to do a formal definition of a proof. And our formal definition of the proof, we're going to use a template. Now, writing a proof of what a limit is a very stylized, formal way of writing mathematics. So it's got a definite format to it. The equations read like sentences. So we use punctuation marks and we treat them more or less like it's a paragraph. All right. Now I've got the format for you already outlined, and it basically splits the work into two sides, the scratch work side and the non-scratch work side, the formal side. So it's kind of hard to get the whole thing on here. All right. So what we've got here is we've got the word proof underlined, and then the directions prove that the limit as x approaches a of f of x equals L. And then you can see I've got a template here with some highlighted blanks, and you're going to be filling in the blanks and filling in this blank space here. All right. Now, the left side is the actual formal proof side, and the right side is the scratch work side, but this is where the real work goes on. All right. So the real work is on the right-hand side. So our goal on the right-hand side is to start with the function minus the limit value and to do something to it algebraically where we end up with the value of x minus a in absolute value less than something. We're looking for that. That's our goal on the scratch work side, is to get the absolute value of x minus a less than something. So down here, we're trying to fill in this blank. This is going to be filled in with a, and this is what we're looking for right here on the scratch work side, this delta. We're trying to find delta for the epsilon that's set. Now, most of the time, epsilon is not set to be a particular number like 0.5 or 1. Most of the time, epsilon is left an arbitrary variable, but it is constant for each problem. So what we're going to do is we're going to find an expression for delta in terms of epsilon. The last thing that we put on the formal stylized side are the letters QED, which stands for quo erat demonstratum, which means quite enough has been shown or quite enough demonstrated, or in grad school, we used to say quite enough, damn it, right? Because by the time we got to the end, we were really finished and done. All right. So yeah, proofs can be quite difficult. So let's look at an example where everything is filled in so that you can kind of get a feel for how this works. So we're trying to prove that the limit as x approaches 5 of 4x minus 1 is 19. So we're going to identify the different pieces of the proof. So first off, when you see the limit, x is approaching a. So a is 5. Whatever is sitting next to the limit inside of it, that's the function, f of x. And whatever it's equal to, that's L. All right. So we're defining some of the pieces in the formal definition and in the scratch work side. A is 5 because that's what x is approaching. F of x is 4x minus 1 because that's what's inside the limit. And the limit value L is 19 because that's what the limit is equal to. Then we start on the scratch work side. The little yellow boxes are showing you what order the work is done in. As in, this is done first, this is done second, this is done third, fourth, and so on. All right. So when we start with f of x minus L in absolute values less than epsilon. So you'll see right here that we have 4x minus 1 minus 19. All right, that's where we start. We always start in the same place. It's always the function minus L, and it's always an absolute values less than epsilon. Then the next thing that we're going to do is we're going to combine the constants, -1 minus 19, and write it as minus 20. This is the third thing we do. Okay. The fourth thing we do is we factor the 4 because we have a common factor of 4 inside the absolute values. We factor it out. Once we've pulled the 4 out of the absolute value of 4 is, of course, 4. And then we're going to divide both sides by 4. Note that the absolute value of 4 is 4. So you could just divide by 4 instead of the absolute value of 4. All right. This leaves us with x minus 5 less than epsilon divided by 4. This is what we were after. Our entire goal on the scratchwork side is to come up with an expression for x minus a less than something. All right. And we don't know what the something is, but we know it'll depend on epsilon. So 5 was our a up here. So once we factored out the 4 and divided by it, we had x minus 5, which was our x minus a. And that is going to be less than epsilon over 4. So the whole purpose of the scratchwork side is to start with f of x minus L, do some algebraic tricks, and get x minus a. Take whatever it's less than and choose that to be your delta. So now we start the formal definition. All right, step 10. Let f of x equal 4x minus 1, comma, and let epsilon be greater than 0. Remember that epsilon is the distance away from L on our graph. It was the horizontal band, right? So it was the width of half of the horizontal band. So we went epsilon up and epsilon down from the center. Choose delta greater than 0 equal to epsilon over 4. This value right here came from the scratchwork side over here. All right, that's 11. Such that if 0 is less than x minus, this is a, all right, so we're going to put a there, less than delta, then, and the next steps on the formal side are exactly the same steps as you have on the scratchwork side, but in the reverse order. So you're basically undoing the work that you did on the scratchwork side to end up with f of x minus L again. So we start with absolute value of x minus 5 less than delta equal epsilon over 4. We multiply both sides by 4. That gives us 4 times x minus 5 less than epsilon. Distribute the 4, 4x minus 20. Then rewrite negative 20 as minus 1 minus 19 so that we get f of x minus L. So this is our f of x. And this is our L, all right? And then we end up with f of x minus L less than epsilon. That completes the proof. And we then restate it. Thus, the limit as x approaches 5 of 4x minus 1 is 19. And then we put QED at the bottom to indicate the end of the proof. So you have two sides. You have a scratchwork side, where the work is really happening to find the value of delta depending on epsilon. And then the formal stylized side just sort of sets things up in the appropriate order to do the proof, right? So if you want to see what it looks like without the yellow boxes or the underlining, it looks like this, all right? So you're starting again with f of x minus L, doing algebraic tricks to get x minus a, take what it's less than to be the value of delta, start with x minus a less than delta, and build the same algebraic tricks backwards to get f of x minus L. Thus, the limit is 19. I'm done. All right, QED. Quite enough, damn it. All right. So let's start with our first one. You'll see that I've got a template for you to fill out here. And this is what it'll look like more or less on the exam, just without the purple stuff. All right. So when we're looking at this, we want to go ahead and fill in the different pieces. So we have the limit as x approaches -1 of 4x plus 1 equal -3. So we're going to identify our different pieces. A is -1. the function is 4x plus 1, and L is -3. So we're going to start on this side with f of x minus L. All right, so we're going to come down here and we're going to have absolute values 4x plus 1 minus, that's the formula, -3, that's the value of L, and set it less than epsilon. Be very careful with your signs. The formula itself is subtracting L. That accounts for one of the minus signs. The other one is in part of L, which is a -3. So we have a double negative. That's really important. The next thing that we're going to do is we're trying to get x minus a. So we're going to write down here what x minus a is. So x minus a would be x minus -1, right? So we're hoping to end up with x minus -1 if we get it to work, all right? So we're starting with f of x minus L, which is here, and we're aiming for x minus a, which is here. And we want to know what this is going to be less than. This is less than something. We don't know what it is yet. Okay. So the first thing you would try algebraically is what? I mean, what does it occur to you to do?
Add.
Add.
Constant.
Okay. So I have a double negative that makes it plus. So this is going to give me 4x plus 4 less than epsilon. All right. Okay. Someone else tell me what you would do next. What might be the next step?
Factor out the 4.
Factor out the 4. So I'll take the 4 off of the x and the constant. That gives me x plus 1 less than epsilon. I can also take the 4 out of the absolute values. Okay, someone else tell me now, what should I try next? What is the absolute value of 4?
4.
4. And what should I do with it?
Divide both sides by it.
Yep, so let's divide both sides by 4. So this is going to give me x plus 1 less than epsilon over 4. Is x plus 1 the same thing as x minus a -1?
Yes.
Yes, then I'm done. I've got x minus a, and this epsilon over 4 that I have here, that's what I'm going to choose to be my delta. So I'm going to choose that for my delta, and now I'm going to come and write the rest of the proof. So now we're going to fill in the formal side. So this is my delta, which is going to be epsilon over 4. So let f of x be 4x plus 1, and let epsilon be greater than 0 as a distance. Choose delta to be greater than 0 as a distance, equal to epsilon over 4, such that if 0 is less than x minus, this should be a, -1, less than delta, then we have x plus 1 less than epsilon over 4. I'm going to repeat the steps that I see over here on the right side, but I'm going to do them in the reverse order. So I went from x minus a -1 to x plus 1, and I replaced delta with epsilon over 4, since that's what delta is. Okay, and this should be, oh no, it's already up above. Yep. Okay. Then the next thing that I did, looking at the right-hand side, was I had divided by 4. So to undo that, I'm going to multiply by 4. And that gives me 4 absolute value of x plus 1 less than epsilon, which is the same as 4 times x plus 1 less than epsilon, which is the same as 4x plus 4 less than epsilon. I'm just repeating the steps that I took over here on the right side in reverse. And then I'm going to split my 4 into +1 minus a -3. And this is what I was looking for. This is my f of x, and this is my L. So I've achieved what I wanted right here. My f of x minus 3. Thus, the limit as, and this should be, the limit as x approaches -1 of 4x plus 1 equals -3, period. Q, E, D. Very formal writing, very stylized. Let's do another one. This one is very similar to the one we just did. It's almost identical. Prove that the limit as x approaches 2 of 3x minus 2 equals 4. So A equals 2. F of x equals 3x minus 2. And L equals 4. All right. Now we're going to fill in the blanks. This is f of x minus L. And L, of course, is 4. So we're going to have the absolute value of 3x minus 2 minus 4 less than epsilon. Start with f of x minus L less than epsilon. My goal is to get absolute value of x minus 2. So down here, I'm looking for absolute value of x minus 2 less than something. All right, so that's what I'm hoping to get down here at the bottom. We'll do what we did last time. So go ahead and work through it real fast. This time we get -6. Factor out the 3. So we'll choose epsilon over 3 this time to be our delta. Okay. Now let's start work on the formal side. We start by setting the function, let f of x be 3x minus 2, and let epsilon be greater than 0. Choose delta to be greater than 0 and equal to epsilon over 3. Such that if 0 is less than x minus a, which is 2, less than delta, then, looks like I've got 2 commas in there. I'm not sure why I have 2 commas in there. Then we should have x minus 2 less than epsilon over 3. All right, so I'm going to start at the bottom on the right and work my way backwards. So I'm going to multiply both sides by 3. And then pull the 3 inside the parentheses, or the absolute value. Distribute it. And then break up the -6 into -2 minus 4, so you can get the function 3x minus 2 minus 4. Right? That was our f of x minus L. And then we finish with our definition. Thus, the limit as x approaches 2 of 3x minus 2 is equal to 4. Q, E, D. All right. This next one is slightly different, not difficult compared to the first one, about the same level of difficulty. These are all hard, Don't get me wrong. These are all hard. It's a difficult way of thinking. It's a very advanced, high-level critical thinking type problem. If you're talking about Bloom's taxonomy, you're right at the top. All right, you're at the top of the pyramid. All right, you're analyzing and creating. All right, so this is high-level thinking here, and it's quite difficult. So we have the limit as x approaches 3 of x minus 3 quantity squared. So we start with a equals 3, f of x equals x minus 3 quantity squared, and L equals 0. All right, so my limit value is 0. Don't freak out, just go with it. All right, so I've got f of x minus L is where I'm going to start, less than epsilon. So I've got the absolute value of quantity x minus 3 squared minus 0. That's the limiting value, less than epsilon. The first thing, of course, is when I subtract 0, that's not going to change anything. And I'm trying to get down here to x minus 3 less than something. That's my goal, right? So how can I go from this to getting x minus 3 by itself? Well, the minus 0 I could drop, right? So then I would have absolute value of x minus 3 squared less than epsilon. I have this. I want this. All right. So I have x minus 3 quantity squared. I want a single x minus 3. How do you normally get rid of squares?
Are we
Right.
taking the square root?
Yeah, good. So everybody agrees. We're going to take the square root of that. Okay, so we're going to take the square root of the left and the square root of the right. And because of the absolute values, it just leaves 1 behind. And this is going to be the square root of epsilon. Now, remember, we set epsilon to be a strictly positive thing, so we don't have to worry about taking the square root of a negative. So that means that we're going to choose delta to be the square root of epsilon. So coming up here, we start on the formal side. Let f of x equal x minus 3 quantity squared, and let epsilon be positive. Choose delta to be positive and the square root of epsilon, such that if 0 is less than x minus a, which is 3, less than delta, then, and we're going to start at the bottom and work our way back up to the top. We're going to start with x minus 3, since it's less than delta, would also be less than the square root of epsilon, since they're the same. Then we're going to square both sides. And then we're going to rewrite it with the 0, which is the limiting value. And then the last thing we do is we write the limit again. Thus, the limit as x approaches 3 of x minus 3 quantity squared is equal to 0. And then we put the finishing acronym on it, QED, quo erat demonstratum. Latin, for quite enough has been demonstrated. Okay. Let's take a look at example 5, where we have a slightly different technique being used. So we've seen factoring out a common factor, and we've seen taking the square root of both sides. This one is a little bit different, all right? So we have a equal to 3. The function value is the rational function x squared minus 9 divided by x minus 3, and L is equal to 6. All right. The next thing we want to do is start with f of x minus L. So we're going to start with the absolute value of x squared minus 9 over x minus 3 minus 6, absolute value less than epsilon. We want to end up with x minus a, which is 3. So we want to end up with x minus 3 in absolute values. Now, looking at this particular one, what might you try? What would be a good thing to try? When in doubt,
Factoring?
yeah, Caleb's right. Let's try to factor this. So we're going to factor the x squared minus 9 into x plus 3, x minus 3 over x minus 3. Then we have the minus 6 less than epsilon. What happens to the x minus 3s? They'll
Goes
cancel.
away.
Yeah, they go away. Thanks, Sean. So then we get x plus 3 minus 6 less than epsilon, which gives us x minus 3 in absolute value less than epsilon. We didn't have to do anything to the epsilon side. It just worked out that it ended up being the same as what it originally was. So we will choose delta to be epsilon itself. All right, so now we start the formal side. Let f of x equal x squared minus 9 over x minus 3, and let epsilon be greater than 0. Choose 0 less than delta equal to epsilon, such that if 0 is less than x minus a, which is 3, less than delta, then x minus 3 in absolute value is also less than epsilon, since epsilon is delta. Now we work our way backwards. So we have x plus 3 minus 6 less than epsilon, which is the same as x plus 3 times x minus 3 over x minus 3 minus 6 less than epsilon, which is the same as x squared minus 9 over x minus 3 minus 6 less than epsilon. So you're literally rewriting the same steps, but backwards on the formal side. You're starting with x minus a, and you're proving that that means f of x minus L is less than epsilon. If you can fit within delta distance of 3, then the function will fit within epsilon distance of 6. Right? If you can get the band around 3 on the x-axis close enough, then the horizontal band around 6 will land all the y values within epsilon of 6. And then we rewrite the final value again down here. Thus, the limit as x approaches 3 of x squared minus 9 over x minus 3 equals 6. And we put the ending acronym QED. Okay. Let's see. There's one more that I want to work today, which is a little bit different. It's very like the last one we did, much like the last one. A little different, but mostly like the last one. So we want to prove the limit as x approaches 2 of 2x squared minus 3x minus 2 over x minus 2 equals 5. So we have a equals 2. We have a more complicated rational expression for the function. And our limiting value is 5. So we're going to start with the absolute value of 2x squared minus 3x minus 2 over x minus 2 minus L, which is 5, less than epsilon. We're going to do the same steps that we did last time. It looks to me like factoring is probably the way to go again. So you're going to factor the 2x squared minus 3x minus 2, which should give us, I think that's a 1, and that's an x. I think that's a 2. So that will give me a 4x and a 1x, which has a difference of 3x. So that should be minus, and that should be a plus. You're guided somewhat by the denominator because you're hoping it will cancel with the x minus 2. And of course it does. All right, they're not all this easy, by the way. All right, and that gives us 2x plus 1 minus 5 less than epsilon, which gives us 2x minus 4 less than epsilon. I'm running out of space. And what should we do now? What are we trying?
Divide those sides by 2.
Yes, we need to factor that 2 off and get it out of there. So we have a 2 times x minus 2 less than epsilon. I'm running out of space, so I'll put it over here to the side. X minus 2 less than epsilon over 2. So we're going to choose delta to be epsilon over 2. Right? So this is sort of a combination of the first method and the last method that we saw, where you needed factoring and you needed factoring out the common factor, right? So we're going to start up here with the function. Let f of x be 2x squared minus 3x minus 2 over x minus 2. And let epsilon be greater than 0. Choose 0 less than delta equal to epsilon over 2, such that if x is not equal to a but close to a, where a is, what was a? 2, less than delta, then the absolute value of x minus 2 is less than epsilon over 2. Then we go backwards to absolute value of x minus 2 less than epsilon, which gives us 2x minus 4 less than epsilon, which gives us 2x plus 1 minus 5 less than epsilon. I'm just repeating the steps backwards, which gives us in absolute values 2x plus 1 times x minus 2 over x minus 2 minus 5 less than epsilon, which is the function 2x squared minus 3x minus 2 over x minus 2 minus 5 less than epsilon. All right, so we've got the whole thing there. Okay. And then we rewrite the limit. Thus, the limit as x approaches 2 of 2x squared minus 3x minus 2 over x minus 2 is equal to 5. And then we put the ending acronym on it. Okay. Now there are much more difficult limits that we can do, and I will do those as well, but I will spread those out over different days. The one I'm going to give you on the exam will be just like the previous ones that I've done, right? So look for one like examples 1 through 6 for the exam, all right? The others I'll do as examples, but I'm not going to harp on it too much. Okay. There are a couple more things that I want to talk about, which is proof of a limit law and one-sided limits. So let's take a quick look at those things. I don't want to take too long. We're going to get way behind here, but that's okay. If we get behind, we'll just push things off a day and we'll make it up down the road. I know we'll make it up down the road. This first part's a little difficult. I tried squishing it tighter together. It's just not working. Okay, so we're looking at the triangle inequality, which says that if you add two numbers together and then take the absolute value, that's got to be less than or equal to the absolute value of each one then added together. And the reason is because imagine if you had a negative number, if you had like 5 plus a negative 3. Well, if you added them first, it would get smaller and become 2. Whereas if you did the absolute value of 5 plus the absolute value of 3, you'd get 8, right? So imagine, if you will, that you had something like 5 plus a negative 3. That's got to be less than or equal to the absolute value of 5 plus the absolute value of negative 3, which this is 8, and this is 2, all right? This is called the triangle inequality. And it's a way of saying that basically two sides of a triangle have to be longer. If you add the two sides, it's got to be longer than the third side that connects them. All right. Okay. So we want to do a proof of the sum law of limits. Now that we have our formal definition, the epsilon delta definition, so we're going to start with a function f and a function g, and we want to prove that the limit of f of x plus g of x is equal to L plus m, where L is the limit of f of x and m is the limit of g of x. All right. So we did not prove the limit laws when we stated them earlier in section, I think it was 2.2. We just stated them. We didn't actually prove them. So we start with let epsilon be greater than 0. And notice that we're using punctuation, and it does sort of read like a paragraph. This is a proof. Choose delta 1 greater than 0, so that if 0 is less than x minus a less than delta 1, this is just like the proofs we've been doing, then f of x minus L is less than epsilon over 2. So this time, instead of being less than epsilon, we're choosing for it to be less than half of epsilon. We'll choose delta 2 so that if I'm in the same range, x minus a less than delta 2, then g of x minus m is also less than epsilon over 2. Notice we need two delta values because we have two different functions, and they could have different intervals that make them be within epsilon over 2 of the limiting values L and M. Then we apply this technique here where we simply choose the smaller interval of delta 1 and delta 2. So if you will, imagine that you've got a graph and you've got two functions. Maybe I should make them different colors. So we have an f of x and we have a g of x. And we have a right here. All right. So coming across, the limit of g as x approaches a is m. And the limit of f as x approaches a is L. So these are different values. And I want to be within epsilon over 2 of each one of these. All right, so I've picked some band around these where I've got epsilon over 2. All right. Now, the next thing that I want to do is I need to pick a delta 1 around this. So delta 1 goes with the f function and delta 2 goes with g. So let's suppose that delta 2 is here and delta 1 is here. All right. So we're looking up here, going to the f function, and it's creating these bands to fit within there. All right. That's basically what we're doing. So we've got two regions around A. We've got a delta 1 band and we've got a delta 2 band around G. All right. So when I look at the one around G, it comes up to here and it's fitting within there. And oops, that went off a little bit. This one actually goes to the upper one. And this goes to the lower one. All right, so we've got our two bands there. The trick to this one, or the technique to this one, is to choose delta to be the smaller of delta 1 and delta 2. If it fits within the smaller one, which is here, delta 2, then it definitely is also within the larger one, right? So look over here at the blue band. The blue band is fitting here. So I'll outline the blue band a little better. Here. Here's the blue band. And then we've got the pink band, which is on the same spot there, but on a different spot here. If you fit within the smaller band, aren't you still within the blue band? Yeah, you are. If you pick the smaller one, then you're in both of them. So we pick the smaller of delta 1 and delta 2, and we let that be delta. Then we assume that x is within that delta distance, this yellow highlighted distance here. So as long as it's within there, it should fit within both regions to land our y values within epsilon over 2 of m and l. So that lands in both of those regions over there. All right. Then we can say that the limit of f of x plus g of x minus l plus m, and again, this is nothing more than our function f of x minus L from the original proofs that we were doing. So we take our new function, which is f of x plus g of x, and its limit, L plus m, and we subtract the two. Now, the next thing is that we can rearrange the order that these are written in, and we can write f of x minus L plus g of x minus m. So this is just rearranged terms. And then we use the triangle inequality. So this step right here is the triangle inequality. All right. So we said that the sum of these two in the absolute value has to be less than or equal to the absolute value of each individual one. But each individual one we know is within epsilon over 2. And when we add the epsilon over 2s, it's less than epsilon. And that proves that the sum of the limits is the limit of the sums. Okay, did I say that right? The limit of a sum is the sum of the limits. Okay, and you can do this for all of the proofs, but we're only going to go through one of them. We also need to define our one-sided limits. In our one-sided limits, the only change that we need to make is we don't need absolute values. We just need to make sure that we use the correct side. So this is the limit from the right, where you're only coming at x values that are greater than a. So you have x minus a greater than 0, less than delta. You don't need the absolute values because you know they're bigger than a. They can't be smaller for the limit from the right. On the limit from the left, you know that the x values are on the left side of a. So you know that they are smaller than a. So x minus a is negative. And so they're less than 0, greater than negative delta. And that's the change that you make for the one-sided limit. I will not be asking you to do any proofs with one-sided limits. I just do want to point out that you can rewrite the rule so that it does work for limits from the left and limits from the right. I do have an example in here, but in the interest of time, I'm going to skip it. All right. And then we have infinite limits. And we want to talk about the idea of the infinite limit. We're not going to get into great detail, but we want to talk a little bit about the idea. How do you define an infinite limit where it's not approaching L, it's approaching infinity, all right, or negative infinity? How do you quantify that? How did Cauchy make this mathematically precise so that he could prove it? So what he did was he made a requirement that you can get closer and closer to A. And if you get closer to A, then your value gets over some M value, all right? It gets larger than some set M. And no matter what you choose, you can always make it get larger. If you can always make the Y value get larger, then it must be approaching infinity. And that's the idea. So here's the formal limit. Let's read through it. A lot of it's very similar to what we had before. Let f of x be defined for all x not equal to a. We only want to be at a in an open interval containing a. Okay, just like the picture up above. Then we have an infinite limit as x approaches a of f of x equal to infinity if for every m greater than 0, choose your favorite ginormous number, there exists a delta greater than 0 such that if I am within delta of a, then f of x is bigger than that m. All right, so let's say I pick this number right here. Then coming over to the graph, I would set this smaller distance here to be my delta. All right. If I choose this for m, I come over to the two sides of the asymptote. I come down to where they hit the axis. They create distances from A, and I choose the smaller distance to be delta. And then as long as the x values are closer to A than that delta, then their value is going to be bigger than m. They're going to go up even higher. So if I choose this value in here, which is closer, it's off my screen, it's so high. All right. So as long as you choose that, it will definitely go up. All right. That's the idea of the formal limit for infinity. For negative infinity, the only change you have to make is that for every m you choose greater than 0, the function value will be less than negative m. In other words, below it. All right. So those are the ones that we, or the way that we define those. Then we can talk about limits at infinity. How do we write an infinite limit at infinity? We say that a function f has an infinite limit at infinity, and we write the limit as x approaches infinity of f of x goes to infinity. If for all m greater than 0, that's the y value again, there exists an n on the x-axis such that the y values are all bigger than m as long as I am past n. In other words, no matter what huge, enormous number you choose for m, I can find an n on the x-axis where all the values past that are bigger than m. And that means the function has to be approaching infinity as the end behavior on the right. Okay. And then we can say the similar thing for approaching negative infinity. All right. And here is an example of a proof of that. I went ahead and wrote it out for you. We have the limit as x goes to infinity of 3x squared. Remember, 3x squared, of course, is a narrow parabola. It's going up 3 times as fast. So as you move to the right, the function is definitely going to infinity. This is your scratch work over here on the right. You start with x greater than n. Then you say x squared is greater than n squared. So 3x squared is greater than 3n squared. And you choose m to be 3n squared. Then n squared is going to be m over 3. So n is the square root of m over 3. All right, so this is your scratch work side. And again, I will not ask you for one of these on the test. All right? Okay. There are limits, of course, that do not exist. So what does it mean to have a limit that doesn't exist? It means that the function for every real number L and for every epsilon greater than 0 and all delta greater than 0, as long as you're within delta of x, your y value is greater than epsilon away from L. All right. In other words, it doesn't settle down and approach that one value. So in the next video, we'll take a look at some difficult epsilon delta proofs.